In this video I talk about boundary value problems and how to solve them with Matlab. The video is based on the example boundary value script. We start at line 3. We define some defaults, we clear the workspace, we close all the figures. Now we are ready to find the equation. The equation I use for illustration is of the Euler-Cauchy type, so it's bound to have an explicit solution in terms of elementary functions, and you can see the equation in line 2. It reads x squared times y double prime plus 3 times x times y prime plus 4 times y equals 0. We first define the equation symbolically. So the expression eq is now the left-hand side of the equation. I also define the corresponding LaTeX string. This will be used later for the title. We already know how to convert this single second-order ODE to a system of two first-order ODEs. So we first reduce the differential order, we convert to mass matrix form, we solve for the first derivatives, and we convert the right-hand side to a function handle fh. You can see the function handle in the command window. Since we deal with a boundary value problem, we have to define the lower boundary. I've chosen a equals 2, and an upper boundary, I've chosen b equals 8. And now we are ready to loop over 3 different cases, 3 different types of boundary conditions. Let's start with the first one. We define two numbers, 4 and -1. We put them in the vector y0 or y0. Now what do they mean? What do these numbers mean? Well, we want the function value at the lower boundary a to be equal to the first element of y0, and we want the function value at the upper boundary b to be equal to the second value in y0. So y of a should be the first element equals 4, and y of b should be the second element -1. In line 29 we can express these boundary conditions symbolically. This will then be used for the symbolic solution of this boundary value problem. For the numerical solution, we have to define two function handles. The first function handle, it's called bcres. The name doesn't matter, you can choose any name you like. This function handle expresses the same condition in a slightly different way. The arguments of bcres, of the function bcres, are ya, yb, and y0. Now, ya is a column vector of 2 entries, of 2 functions if you want. The upper entry, the first row, is the function value at the point a, at the lower boundary, and the second entry in the second row is the derivative of y at x equals a. And similarly, yb consists of the function value at b and the first derivative, or the slope, at b. Now B0s expresses the condition that ya of 1, which means the function value of a is equal to the first element of y0, and the function value at b is equal to the second element of y0. As usual, we can drop the equal 0 sign from these conditions. So line 29 and line 31, in fact, express the same conditions. Next, we have to define initial guess of the solution. This initial guess is computed via the function handle yInit, and yInit also has two rows. In the upper row, we have a function of x, and in the lower row, in the second row, we have the derivative of this function. Now, the initial guess is not always obvious. In simple cases like the present one, it's sufficient to use some non-constant function of x. So I've chosen a straight line as initial guess. You will see the solution is very far from a straight line, but it works. So the initial guess is a straight line through the two boundary points at the given function values. And this is now expressed by the function handle yInit. So yInit is a function of x, and it's a column vector. The upper entry is the function, and the lower entry is the derivative of this function. We are now ready to first solve the problem symbolically. We have already set up the symbolic boundary conditions in the symbolic vector bcont, and we'll get the result in the structure solsym. We simplify solsym and convert it to a function handle. Let's have a look at solsym, or at the simplified version of solsym. It looks like this. So it contains the elementary functions sine and log. Now we proceed to a numerical solution. We first define a grid in X between the points A and B, and the solution will be computed on this grid. So this is the vector X init in line 61. In line 62, we now compute a structure sol init. This is returned by the Matlab function bvp init, which takes as arguments the grid x init and the function handle y init. Sol init is again a structure which contains the name of the function that was used to generate it, which was bvp init. It contains the grid x, and it contains the initial guess and its derivative in the function y. So first row is the function, second row of y is the derivative of this initial guess, and it also contains the function handle that was used to compute this initial guess as a function of x. Now we can finally invoke the solver. It's called bvp for c, and it takes 3 arguments. The first argument is the function handle, which defines the right-hand side of the system of first-order equations. The second argument is the function handle that computes the residuals of the boundary condition, so the difference between the actual value and the prescribed value. So these residuals should be 0 or very close to 0 when the solution has been computed. Now in our case we have defined the function handle bcres as a function of ya and yb and our vector y0, but BVP4C expects a function handle that depends only on ya and yb. So we create this anonymous function which specifies the function handle bcres using the actual initial boundary values y0. And the third argument is the structure sol_init that we have created in the line before. So let's invoke the solver. It's very quick in this case. Let's have a look at the output structure. I call it sol_num, and it contains the following fields: the solver that was used to compute the structure. It contains the grid in X. It contains the function values and the derivative of the function in the matrix Y. And it contains again the derivative and the second derivative in the matrix YP. And then it contains some statistics. Let's have a look at these statistics. So we had 101 mesh points. That was the dimension of X in it. We have the maximum residual at the boundary. We have the number of evaluations of the ODE and the number of evaluation of the boundary conditions. Now we can extract the grid in X, which is actually equal to X in it, and we can extract the solution. Now we are ready to plot the solution. Let's open a figure. Plot the solution in blue. So this is a solution. We'll check in a minute that it actually fulfills the boundary conditions. We also extract the first and the second derivative, and we can now compute the left-hand side of the equation. And this array LHS should be very close to 0. Let's have a look how far it deviates from 0. LHS. So it's equal to 0 within a few times 10 to the minus 15. So if we plot now the left-hand side of the equation, which is to say x squared times second derivative plus 3 times x times first derivative, which we see here, plus 4 times the solution. This is the left-hand side, which is virtually identical, equal to 0. So this is the dashed line at 0. Let's put some labels And let's put a title. So the title says solution of this equation with y of 2 equals 4. Okay, we see the function value at 2 is actually 4. And the function value at 8 should be minus 1. And this is true as well. So the boundary conditions are fulfilled. Let me just shift the title up a bit. Now let's also plot the symbolic solution, and you will see that the two solutions coincide perfectly. Let's put a legend. So blue is the numerical solution, green dashed is the symbolic solution, and the left-hand side is the black dashed horizontal line at 0. So this solution is perfectly satisfactory. Now let's look at the other types of boundary conditions. In the second case, we have the following condition. The value at the lower boundary should be 5, and the derivative at the upper boundary should be 2. So in symbolical form, this reads like this: y of a equals 5 and dy of b equals 2. What does it look like in the function handle bcrs? Well, ya of 1 is a function value at a, and this should be equal to the first element of y0. And then we have yb2 in line 41. This is a derivative at the boundary b, and this should be equal to the second element of y0 equal 2. So we want the function value at a equal to 5 and the slope at b equal to 2. We use the same initial guess. Okay, let's go right to the end of the loop. So let's have a look at figure 2. So we now ask for a solution with function value 5 at x equals 2. This is the case. And we want the slope at the upper bound 8 to be 2. And this is also true. Okay, now let's go to the third and last example. We now specify two slopes. The slope should be minus 5 at the lower boundary, and the slope should be 0 at the upper boundary. So this is expressed in symbolical form like this: dy at a should be minus 5, dy at b should be 0. And in the function handle bres, we ask ya of 2, that's the slope at a, should be equal to 5, first element of y0, and yb2, the slope at b, should be equal to the second element of y0, which is 0. We still use the same initial guess, a straight line. And this is the third solution, and we now have the following boundary conditions. Slope at 2 should be minus 5, and slope at 8 should be 0. And you can see that this is actually the case.